Itself. So you first start by just writing its same thing down. And then you have to multiply by the derivative of what's up here. And that is a composition. That's sine of 5x. So you take derivative of sine of something, it's cosine of that something. And then times, where's the 5 come from? You have to take derivative of what's in here, right? Yeah. So that's 5. And again, you could move the 5 out front or whatever. All right, number 7. This is, I kind of reversed the order here. Now I have sine of e to something. So you start with the sine. Derivative of sine of something is cosine of it. Times derivative of what's in here, itself. Times derivative of what's up here. Here. 8. Make sure everyone's comfortable with what the derivative of natural log of something is. Derivative of natural log of something is 1 over it, right? So you have to just write 1 divided by whatever the argument is, everything in here. Then chain rule says times the derivative of what's in here, and what's in there is a product rule again, right there. So you must do that product rule. And that product, you know, take derivative of this, put it here, times this, plus derivative of this, times this. And do I have to have parentheses here? Absolutely have to have parentheses here. Because this whole thing would distribute to both of these. Now the other thing you could do is take this whole expression and move it up on the numerator. That would be fine. But if you're going to leave it off to the side like that, it all has to be in parentheses. All right, number 9. Number 9 has to do with like a related rate problem where you differentiated an equation with respect to time. So we wanted to know what dr dt is. So we look at this equation and we realize that pi is a constant, right? Pi times r is a variable, right? It depends, we're saying the r depends on t. So the derivative of this, the pi comes along for the ride. Then we do a little power rule on that. What's the derivative of r squared? That looks like r cubed almost, doesn't it? Yeah. If you use cubed, it's okay. If you use cubed, then this would be 3 and this would be r squared, okay? It does kind of look cubed. Sorry. All right, so the derivative, let's say r squared though. Derivative of r, how many of you use squared? Everyone use cubed? How many of you use cubed here for this? Some people didn't get to it. Okay, whatever. Never mind. The important thing is that when you take the derivative of this, the power comes out and you reduce the power by 1. But then, very critical, this piece. That's the derivative of the base. You have to take derivative of r itself. And the derivative of r with respect to t is dr dt. It's not 1, it's dr dt. Then you move to the other side of the equation and you have 2 more variables that are depending on t also. So you have to use product rule. So you take the derivative of this one with respect to time, dA dt, times the second one, plus the derivative of w with respect to time times the first one. And that gives you an expression, an equation. And then you need to isolate dr dt. So to do that, all you do is take this whole side, right there, and just divide by this right here. Just divide both sides. Did I forget the r? I did. There needs to be an r there. Whoa. My pen's not working. That doesn't happen often. Oh well. Okay, and then the last one. The last one is implicit differentiation. Number 9 and 10 were both implicit differentiation. So I don't really want to go through this whole thing. But we had a product rule here, so I had to do that here. Here, the derivative of sine of y, that's an important one, because the derivative of sine y is cosine y. But then the chain rule says you have to go and take derivative of what's in here, and that's where the y prime comes from. And remember, y prime is the same as dy dx. So I'm using the different notation there. All right. Did I mess? I threw this real quick together. Where's the x squared?
Whenever you take the derivative of x squared, y cubed, you should have an x squared on the right side with y prime. It should be. That's x squared for you. Yeah.
Wait a minute, this one right here. Are you talking about here? Let me just look at it. 2x y cubed plus 3. Oh, right there. Yeah. Right there. X squared. Yeah. Well, I was trying to rush through this. No excuses. We're all human. I just was anticipating no one was going to get to that one. Okay. All right. So you got your grade? Top of the page? Give yourself a grade. And then let's hand them in. Remember, be true to yourself. Okay. Make sure you give your pens back to the people you borrowed them from. You can keep the markers. I don't care about that. Man, I wish I could do this for everything I give you. Just have you grade your own. Man, that would make my life so much easier. All right, let's go. It shouldn't take you forever to grade this. We need to move on. Yes, yes? Thank you.
And there's an extra one in there.
Okay. Okay, thank you. All right, I have two more things to talk about before we start the lecture. Bonus. People in my other class were asking about bonus, and you may have gotten something through Canvas. I'm not sure how this actually works, but I'm going to offer everybody in the class a 5-point bonus on your final exam. So it's like a half letter grade. But here's what you have to do. You have to come in and sit down with me face to face in my office for 10 minutes, and I'm pretty much just going to kind of like try and figure out like where you are in terms of, I might ask you like, hey, let's work through a problem. Or I might, we might talk about you work 40 hours a week and, you have 8 kids and you're taking 36 hours of college credits. We may talk about, your work life and how you're trying to balance school and work. We might be talking about math. It's just so, I just want to have an opportunity to know my students a little more. It's difficult just coming in and leaving, to actually know what you're actually going through and even know like what level you're at. Because you may be doing great at home and then you come in on the test and you just like, it all falls apart. So if I know that we've sat down for a little while and I kind of know you're capable of it, and then your test doesn't reflect that, it just kind of helps me, I guess. So it's optional, of course. You don't have to do this. And I'm going to do it during my office hours. So does it show up on your Canvas? So what does it do? Does it like give you a message or something?
Yeah, it sends an email and ask you to set up a time.
It gave you an email?
Mondays and Wednesdays.
Okay, so the way it's, I'm going to set this up where I'd like to do this sometime in the first like 6 weeks. I'd like to get it all done with all my students. So I sent out this thing, and right now it shows only Monday and Wednesday. I need to go, because I have to go and I have to fill in each day, and it's a pain in the butt. It takes me a while. So I'm going to go in there and I'm going to fill it out for the next 6 weeks. There will be time slots throughout my office hours, which are on Mondays, Tuesdays, Wednesdays, and Thursdays. You reserve a slot, and then you just show up, okay? Now, if you reserve a spot and don't show up, you just need to let me know, all right? So what I'll do is, like I said, if we have a nice productive session, then I'll give you 5 points on the final, and this will become an automatic 100. All right? Got it? Any questions on that?
If we aren't available during your
Okay.
normal office hours?
Yeah, so if you can't make my normal office hours, we'll have to set up something special. So it'll maybe on a Friday or maybe at a different time on Monday through Thursday. Because I am around and we can set something up. All right, so just let me know. Email. Any questions about that? Yep. Okay, thank you. All right, so what I would take away from that, no matter what your grade was on that, I look at these problems to be, at least the first 5. I would expect that you could do, the first 5 with relative ease. Maybe you got a little hung up on this one, but these first 5 are like low level to maybe approaching medium level, like not that much, all right? And remember I said we're going to do antiderivatives here, right? So like if this derivative is giving you all sorts of grief, then it's unrealistic to think that you're ever going to go backwards from this to anything reasonable. Does that make sense? All right, so that's it. We're going to put that one to sleep. And then the other thing I want to talk about is why do we do this? Like, why are we doing calculus 2? Your whatever your degree is in. Like, why do we have to do Cal 2? And are you ever going to be doing integration and differentiation when you get your real world job? And I hear that a lot. So, like, what's the value of doing all this? And I kind of understand that. I get that. But I talk to I have a lot of friends who are engineers and computer scientists out in the real world doing jobs that required electrical engineering or, all these different majors. And I talk to them a lot about, what should I be telling my students who are taking Cal 2 or like trying to figure out why I need to do this. And they all pretty much universally tell me the same thing. It's about critical thinking and problem solving. That's what it's about. Because in the real world, that's what a STEM major, if you're in a STEM field, it's going to be critical thinking and problem solving. Your boss comes to you with a problem, or your company takes on a problem, and do you have those critical thinking skills? Are you a problem solver? Are you like, oh, let me go to Chegg. They might be able to build that bridge for me. You know what I'm saying? Chegg is, I think, a site that has the answers to a bunch of problems, right? You know what I'm saying? Like at some point, you can't go find the answers somewhere else. The answers have to come from you. And if you're not a good problem solver, well, then your company will get rid of you pretty quickly. Right? So that's what we're trying to develop in here. An ability to solve problems, long problems that involve all little meticulous details that we can't overlook. All those sorts of things become important later on. So you're developing your mind more than you are like, don't think about it as, like, why do I need to really ever take the derivative of sine? It's this one. There's a lot going on here. It's composition of functions. You're having to process all that information, right? It's deeper than just the mechanics of it. It's the way you think. Does that kind of, am I making a point? Okay. I'll tell you, I'm gonna run out of time again. Dang it! I'll tell you, my brother's an electrical engineer, and for some of you I've had before. So if I told this story, I apologize if you're hearing it again. Did I tell you all about the interview? Yeah. So he had a job interview, and the question they asked him was, well, there was 2 questions. I'll just tell you one of them. They said, real quickly, 2 archaeologists walking down whatever, just walking around. One of the archaeologists goes into a cave, comes back and tells the other archaeologist that he just found the perfectly preserved remains of the first human being. Follow that? 2 archaeologists, one of them goes into a cave, comes back, tells the other one, hey, I just found the perfectly preserved remains of the first human being. That was the story told to my brother at his interview. The question was, how did that archaeologist know that he had just found the first human? That's the question they asked him in the job interview. They didn't ask him to like integrate something or differentiate something. They asked him to think, right? I'll say it one more time. 2 archaeologists, one of them goes into a cave, comes back out, tells the other one, just found the perfectly preserved remains of the first human being. How did he know he found the perfectly preserved remains of the first human being? Anyone have a guess? Or you can't answer if I already told you. Okay, perfectly preserved remains, right? That's key. Perfectly preserved. The body had no belly button, is the answer. What's your belly button? It's tied to the umbilical cord, right? To the mother.
How was it created?
First human would not have a belly button. That's the answer they wanted. You can sit here and go, that's bullshit, man. Look, that's the answer they wanted. Okay, that's the answer they wanted. Do you see that's critical? That's a way of thinking that is just kind of, and actually he got it right. But he also gave him a second answer. He said, my scientific answer is no belly button. My theological, religious answer is no rib. Okay, so, so how do you get to a point where you think like that? You go through these undergraduate programs into graduate programs, and your mind just starts to work a completely different way than it did. Like if I look back at my life when I was in Cal 2, like the way my brain works now is completely different than the way it worked when I was in Cal 2. Just the way I process things is totally different. That's what you're trying to do, trying to develop that. All right, 25 minutes is all I got. Here we go. So I'm blowing through this. 3.5, well, it's good because this is a review. Okay, 3.5, inverse trig functions. You should have studied inverse trig functions in pre-cal, right? Now, I know that's probably been a while, so let's go quickly. Function is said to be one-to-one, and you don't need to copy all this because remember, this is on the web in Canvas. Function is one-to-one if it passes both the vertical line test, oops, I just messed it up. If it passes both the vertical line test and horizontal line test. So if it passes both tests, then it's one-to-one. That means one input goes to exactly one output. You never have one input go to two different places. Is x squared one-to-one? F of x equals x squared. One-to-one? No, because you can plug in 2 and it'll spit out 4. But you can plug in -2, it'll spit out 4. So that's not one-to-one. Now, what we learned in pre-cal was that when you take the standard trig function, like sine, that it's not one-to-one, right? Fails the horizontal line test. But we would love to have a function, an inverse function, that would actually like reverse or undo this function. So the way we got around it, how did we get around it? Yeah, we just restricted its domain. All we did was take that sine curve and cut it off. And we said, if we only look at the sine curve here, then it attains its entire range and its domain is from -π/2 to π/2. In that little piece, it is one-to-one. And then from there, we can define the inverse function. And that's what we did in pre-cal. And this is just going back and reminding you what the inverse trig function is, blah, blah, blah. And there's the graph of sine, and there's the graph of its inverse. Okay. And then we do the same for cosine, tangent, right? Secant, cosecant, and cotangent. They all have inverses so long as we restrict their domains properly, right? That's all pre-cal. But this is calculus. So what do you think we're interested in with those functions? Arcsine, arccosine, arctangent, all those 6 inverse trig functions. What do you think we want to do that we never did in Cal 1? Maybe you did in Cal 1, but if it's calculus, we want to know the derivatives, right? And maybe eventually antiderivatives. But this section, we are talking about what are the derivatives of the inverse trig functions. So if you saw this in Cal 1, great. Some people don't cover this. So that's, at the end of the day, what today is about, is what is the derivative of the inverse trig functions. And in the section 3.5 in your book, it lists out what their derivatives are. All right, so, and also on your formula sheets, they're listed out there, what the derivatives of the inverse trig functions are. But what I'd like to do, is I'd like to actually derive one. I'd like us to actually come up with what the derivative of one of them is, to see the process involved in creating the formula. So we're going to do, let's do this. So let's say that y is arcsine of x. That notation okay with you? Right? And I could also write arc sine of x, right? Both of those notations are equivalent. But I'm going to use this one almost exclusively in this class. All right, so what I'd like to know is what is y prime? So what is the derivative? Well, what we could do is we could take the derivative on both sides, couldn't we? And the derivative of the left would be y prime, and the derivative of the right would be, well, we don't know, right? That's the whole question. So I can't just take the derivative of both sides, can I? So I have to do something else. So what we can do is we can take this equation and we can take sine on both sides. Now why would I take sine on both sides of this equation? Yeah, the sine and the arc sine are going to cancel. There is a property, it's called the cancellation property. It was up in my notes a little bit further. That says that these two will cancel one another out so long as x is within the domain of the arc sine. So as long as the x you're plugging in is valid, then you just cancel out. They just kill each other off. And so all you get on the right side is x. And on the left side you get sine y. Now what's nice about that is that if I take the derivative of this, I know the derivative of sine. Right, it's cosine? But I'm differentiating with respect to x. With respect to x. So the derivative on the left is actually cosine y times what? dy dx. Or I'm just going to call it y prime. Is that all right? That's the same as dy dx. That's the chain rule. It's critical that we understand that this is a y prime and not a 1. All right, equals. Now I can take derivative of this. What's the derivative of x with respect to x? That is 1. So we're trying to find out what y prime is, right? And there it is. So if I just divide both sides by cosine, I get this, and 1 over cosine is the same as secant. It's the reciprocal, right? So my answer is secant y. But that is not the formula you're going to see in the back of the book. Because our answer has y in it, and the original function y equals sine of, arc sine of x, our answer, it would be nice if it had x's in it, because our original function had x's in it. Does that kind of make sense? So is there a way that we can somehow get rid of this y in here and replace it with something with x's? Substitute? Okay, yes, I think I am going to agree with you, but I'm going to kind of handle it in a slightly different manner, okay? I'm going to use something called a reference triangle to do this. And the reason I'm doing this, the reason I talk about this section is because we are going to use reference triangles a lot in this class. So I wanted to show it to you on this first day. All right, so here's where we are, right? We like this in terms of x instead of y. So now what I do is I go back and I take a look at this equation right here. See that equation? All right. What I'm going to do is I'm going to think back to pre-cal and what the definition of sine was on a right triangle. Sine, by definition, is opposite over hypotenuse, isn't it? So if I look at this equation, I could say, all right, sine of some angle y is equal to x over 1. That's the same expression? Yep. And so I could say, look, the opposite side of the angle is x, and the hypotenuse is 1, and the angle is y. So if I draw a y here, and an x here, and a 1 here, do you agree that that right triangle is a visual representation of this equation? Yes? Yep. Now, why am I doing that? Because I want to know what secant of y is. Right? And from this triangle, what would secant be? Secant of y? Well, it's the flip of cosine, isn't it? Yeah. And cosine is adjacent over hypotenuse. Now, we don't have the adjacent side, right? But could we get it? Yeah. Yes, because we're only missing one side of a right triangle. So we could get this. And I know in pre-cal, you did that quite a few times. So I'm not showing that work. So this is the adjacent side, here's the hypotenuse. So if I say what is secant y, this would be not adjacent over hypotenuse, but hypotenuse over adjacent. So this would be 1 over square root of 1 minus x squared. And that indeed is the derivative of arcsine of x. All right? Y'all okay with that? So it's a couple of things happening when you're trying to find these formulas for these inverse trig functions. You undo the inverse trig function by coming, so if this was arc cosine, we would do cosine cosine, right? And then you would differentiate. You'd solve for y prime. You would draw your reference triangle based off this equation, find that missing side, and come back over here. You do the same thing for arctangent. All right, so I'm not going to do those, but just so we know what they are, the most important ones. The derivative of arc cosine of x, anyone know what that is? Negative 1 over square root 1 minus x squared. So it's almost this, right? Just with a negative. And then what is the derivative of arctangent? This one is 1 over 1 plus x squared. And this one I'm going to put a star next to. 3 stars. Or I'm going to go for 5 stars. That's going to be critical in this class, that you understand that the derivative of arctan is 1 over 1 plus x squared. As many times in this class, we're going to find, when we're trying to do antiderivatives, we're going to see this. And we're just going to look at it and go, oh, the antiderivative of that is arctan. As soon as we see it, we're going to be like visually recognizing it, going backwards to this. And you can flip that. You can put x squared plus 1. It doesn't matter. Now there's 3 more, right? We have the derivative of arcsine, derivative of arccosine, derivative of arctangent. There's 3 more, but they're not going to come up very often. But they're in the book, and don't worry about them too much. We good? All right, so with that in mind, let me ask you something. If I say y is equal to arc cosine of root of 1 minus x squared, then what is the derivative? So what I'm getting at here is that I've given you a formula now, right, that we're allowed to use. And now I automatically want us to go and take a look at a composition function and see if you can now apply everything you learned in Cal 1 just using this formula now. So do you all see that we have composition? So the derivative of this would be the derivative of arc cosine of this, right? So it's kind of like, you know, this part right here is what I've circled over there. So the derivative should be negative 1 over square root of 1 minus, and then whatever that is squared. Yes? Okay, so let me write that down. It's going to be negative 1 over square root 1 minus x, not x, but what? So it's this thing squared, like that. Okay? So far, is that all right? Are we done? We are not done. We now have to take the derivative of what's inside, because all we've done is take derivative of the outside function, and that's this. So then chain rule says we multiply that by the derivative of what's in there. So what's in there is a square root, right? And what's the derivative of the square root of something? So this is another one of those ones that I hope that you have like already hardwired into your brain. If somebody gives you a square root of something, the derivative of it is 1 over 2 root something. That's it. Yes, you could do 1/2 x to the negative 1/2. I agree. But every time I take a derivative of a square root in this class, I'm always just going to go right to this. So the derivative of the square root of something is 1 over 2 times root of that something. So the derivative of square root of this is 1 over 2 roots of whatever was in there. Am I done now? No, still have more. Times Now the derivative of what's in here, which is negative 2x. And then there's a lot of things that clean up here. You've got 2 here gone. This negative and that negative right there become a plus. So I'll just make them both plus. And then can you square that square root down there? This right here? When you square the square root, it goes away, right? So what would that be under there? 1 over root 1 minus, what's under here? 1 minus x squared, but you have to have parentheses, right? Or it's going to become positive, yeah. And then the rest of all this, what's that? Yeah, I'm going to bring all this here now. So times x over root 1 minus x squared. And then just clean up what's under here. What does all that become right there? Root x squared. What's root x squared? What is the square root of x squared? It's just x? We have to be kind of careful with that. It's like absolute value, kind of. We have to be a little bit careful with square roots of x squareds. So I'm going to just write absolute value of x, and we can talk more about that later, all right? Like this. The point is, I don't want to cancel these yet. Like, you know, because if x is positive, then this will turn out to be a positive 1. But if x is negative, it's going to turn out to be a negative 1. All right, that's it. I have 9 minutes. I have enough for the last problem. You know how I said I do the homework videos? On 3.5, the video, for some reason on YouTube, it would just freeze. And you would hear the audio, and it was just me standing there. And I deleted the video. I couldn't recover it. So the video that is there is me writing on my tablet. It's not me in front of a board. Just so you know, when you bring it up, you're like, I didn't know they were like this. It's just that first one that's like that. All right? All right, last problem. 8 minutes. While I'm doing this, I need to pass around the sign-in sheet. So hopefully your name appears on this list. Just these are real small boxes. Just put a little initial in there for yourself. If you do not appear on that list, there's space on the bottom for you to add your name. All right? All right, the last problem we're going to do is a word problem. Got to make it a little smaller. A rocket is fired straight up with a speed of 1,000 miles per hour. It's moving. An observer who is a mile away from the launch point is tracking the rocket with binoculars. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? Related rate is what this is. Now, in Calculus 1, we could do this problem. This is actually fair game in Cal 1. So what I'm going to show you is how we could do this with what we learned in Cal 1, and then how we could add what we just learned right now to make the problem easier. So I have to go back and kind of, see where you are when it comes to related rates. And everybody has been taught this different ways. The way that I do it is that when I have a related rate problem, I have my students draw 2 pictures. If possible, draw 2 pictures. The first picture is a picture of the geometry of what's happening with everything moving. The rocket's moving, the guys or girl, whoever, doesn't matter, is looking at the rocket, right? Everything's in motion. So let's imagine I've got the ground here. The rocket has fired up right here. Here's my rocket. Those people who've had me before can testify to my artistic abilities. Yes? Yeah. I'm not humble about it. It's impressive. That's a rocket. That's a rocket. All right. And then we have an observer somewhere down here, which we're just going to represent with a point on the ground. And the rocket's in motion, so I'm going to just label this distance right here from here to here. I'm going to call it y. I could call it r for rocket. I call it anything I want. And I'm going to measure this angle here, theta. Is there anything on that picture that's not changing? The distance from the observer to where the rocket launched from, which is 1 mile. That doesn't change in the problem? Do you agree? Okay, so y is changing, theta is changing. That's my general picture. Now, the picture of the instant in time comes from this question. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? So now what I do is I draw the picture at the specific instant in time. This is 1 and this is 3 now, isn't it? Yeah. And I'll take the time to draw the rocket again. And then now theta is actually an angle, right? It's not a variable anymore. It's fixed. Could you find it? How would you find theta if I asked you for theta right now? Well, what do you know about theta? Tangent of theta is what? Which is? Tangent's 3, right? Arctan both sides? On your calculator, arctangent of 3 would spit back that angle. So at the instant, the snap picture of the moment in time, we know this is 3, we know that's 1, and we know that's some angle that we get on a calculator, right? Okay, so I have my students draw the two pictures. Now what I have my students do is I have them come up with an equation. And that equation, no, sorry, I forgot to put 2 other things up there. I ask my students to write down what they're given in the problem and what it is they want. So what are we given in the problem? The rocket's fired straight up with the speed. Speed is velocity is a derivative, right? So I'm given the rate at which this is changing, right? The rate at which y is changing. So I'm given dy dt. And I'm given that it's 1,000 mph, right? What do I want to know? Okay, how fast, that's a derivative. How fast the angle of inclination is changing. I want to know how fast that's changing. I want d theta dt. And I want that at exactly the moment that y is 3. So now I ask my students to come up with an equation. And this equation, whatever it is, you get to look at this picture, not this one. You're not allowed to look at this one. The equation we have that we come up with must somehow connect theta and y together. And you have to work off of this picture. So can anyone give me a relationship between theta and y? Any relationship you can think of.
It's increasing when y increases, the angle increases?
It does, yes. That is the relationship. We know that when y increases, theta increases. But give me something solid to work with. I need an equation that represents that relationship. Okay, so Pythagorean would be working with these 3 sides, wouldn't it? I don't know what this side is, right? I want an equation that will involve y and the variable theta. Tangent of theta, right? What is tangent of theta according to that picture? Y, isn't it? And now we could take the derivative of this with respect to time. Couldn't we? So let's try it. What would happen if I take derivative of tangent theta? I would get secant squared theta d theta dt. Chain rule. You have to take derivative of what's in here now, right? So derivative tangent something is this. Then derivative of that is this. That takes the left side. Now the right side, what's the derivative of y? With respect to time. dy dt. Okay, what are we trying to solve for? D theta dt, right? That's what we want?
Yep.
Okay. Do we know dy dt? Yes. The only other thing we need to know is this, right? And this is the key to the whole point I'm showing, the whole reason I'm showing you this. And I've got 30 seconds. Can we get theta? Yes, we said we could, right? So in order to give you the answer, I'm going to plug in 1,000 here, and I'm going to find that angle, and then I can solve for d theta. Agreed? But I claim you can do it without knowing theta. And the way you can do it without knowing theta is as follows. Take this equation right here. Take arctangent on both sides. Arctangent. What would happen if I hit this with arctangent? I'd just get theta, wouldn't I? And if I do arctangent on the other side, arctangent y. Now take the derivative. What's the derivative of this? D theta dt. What's the derivative of this? Well, I just gave you the formula for that, right? I said don't forget it. 1 over 1 plus the variable, in this case would be y, squared times chain rule, derivative of this, dy dt. Now, we want d theta dt, don't we?
Yeah.
What do we need to know in order to do it? Y. Do we know y? Yes. Dy dt, 1,000. See, no theta involved at all. We can get the answer without having to ever solve for theta. And that can become useful later. So if you did it this way, you get an answer. If you do it this way, you get the same answer. One of them required the angle, the other one didn't. Okay, that's it. I went overboard, sorry. Sign-in sheet get around? Anybody miss it? All right, so what's due for next class? What should you do? Do the 3.5 homework, and then also go onto that, click on that checkbox syllabus. I understand what's going on. Okay. Have a great day, everyone. I'm just going to squeeze by you real quick and turn my camera off.